Okay, so in this pre-recorded talk, I'm going to discuss Higgs measurements at future circular colliders. This is my contribution to WIN 2021. So of course, my talk is going to be largely guided by my own views and opinions about what to highlight regarding the Higgs at future circular colliders. And there is really an enormous, incomprehensibly almost vast program of Higgs physics that would be undertaken at future circular colliders. And so what I will discuss today can only really scratch the surface, but I'm going to try and link it as best I can to some sort of important big picture questions in particle physics, and also try and give a sort of broad brush view of how future measurements of the Higgs at future circular colliders could change our perspective on Higgs physics. I think it's important to consult the documentation that we already have online. So one example, which I think is fairly comprehensive, is the physics briefing book, but there are many other references these days discussing future circular colliders and Higgs physics. And so, of course, one should consult all of them for a broader picture. Okay, so the big questions we're asking these days in particle physics are where next? The standard model is now established and we have to figure out how to move beyond the current paradigm. My personal view, especially from an experimental perspective, is that the protagonist in the next chapter of particle physics is likely to be the Higgs boson. There are many reasons for this. The Higgs is at the nexus of many of our big questions regarding, for example, naturalness in particle physics, the origin of flavor structures, the origin of the matter-antimatter asymmetry, the origin of neutrino masses. Always in any of these puzzles, although they may seem to be not so directly linked to the Higgs, we find the fingerprints of the Higgs field everywhere. And so it's obvious, essentially, that we should do our best to understand and measure the properties of the Higgs as best as we can to map out the frontier of physics at the next microscopic scales. It's obvious to ask then also, well, how well is well? How good is good? What sort of accuracy should we be aiming for when it comes to measuring something regarding the Higgs? I would say okay is to start to have a precision of around 50%. In sort of layman's terms, that's getting towards 2 sigma evidence for some property of the Higgs. Ideally, we would do much better than that and get to around the 20% level, because then we can start to say that we've really discovered an interaction or a property. So 20% precision, I think, on any relevant Higgs question is sort of an absolute minimum that we should be aiming for in terms of precision. But in reality, we want to know the Higgs as it exists in the path integral, not how it just exists in some classical action. And that means that we need to be able to probe quantum corrections. By quantum corrections here, I mean really ones that probe UV physics and require things like counter terms to perform the calculation. And in the Higgs sector, quantum corrections are electroweak scales, so they're typically around the few percent level. So really, if we're going to claim that we understand the Higgs in the path integral, really the quantum nature of the Higgs, then I believe we should be aiming for around the few percent level. And we should hit that target in as many areas of Higgs physics as we possibly can before we start telling anyone that the Higgs is standard model, like for instance. So how well can future circular colliders do? So there are linear colliders on here as well. I want to show everything at the same time, but FCC is in the last column here, and it's showing a combination of how well you could do on various kappas. So these are modifications of Higgs couplings in the standard model. This is sort of a little bit of a dumb thing to do, where you just take the standard model and change the size of the coupling. That's not really a very self-consistent procedure. Nonetheless, it's not bad as a first attempt at understanding modifications of Higgs properties. And as we see at the FCC, for many couplings to pairs of other standard model particles, kappa W, kappa top even, we get all the way down to the percent level, in some cases well below it. If you look at kappa Z here, you're talking at well below a percent, really the per mil level. So these measurements would be really probing the quantum nature of the Higgs very, very carefully, much like the way we needed the precision LEP measurements to probe the quantum nature of the electroweak sector some time ago. Of course, there is, and there's a great story of complementarity here, by the way, because some of these measurements are best performed at something like FCC-ee. But compared to FCC-hh, that's relatively low statistics. So you see places here where, for example, kappa gamma is actually measured better at high Lumi LHC than it is at FCC-ee, and that's just a question of statistics. But then to really get down to this sub% level requires FCC-hh. Similar stories apply, for example, for Z gamma and so on. Kappa mu. Okay, but we know there's more to life than kappas, and really that becomes increasingly true when we go to hadron colliders. Hadron colliders are really multi-purpose exploration machines. They do not, it is a real injustice to a hadron collider to perceive it as just measuring something like the Higgs coupling to photons. And as we can see, as we go from sort of LHC energies on this plot, this is just for the single Higgs production cross-section and some of the associated production cross-sections. As we go to higher energies at a hadron collider, the cross-sections for Higgs production grow. And what that means, they grow by over an order of magnitude and more in some cases. And what that means is that we can pay a price. We've got so many Higgs bosons that we can pay a price to ask for relatively rare phenomena such as exotic Higgs decays, or we can leverage that high statistics to get high precision in the dominant production modes as well as decays. High precision on these associated production modes. We can access then the tails of differential distributions. We can pay a price of an order of magnitude to go out at large PT, and I'll come back to this. And we can also hope to observe some rare associated production modes as well. For example, you see the ones with much lower cross sections down here. So high energy buys not only precision, but also a really broad Higgs physics program that is not cannot be captured by just talking about a kappa measurement. Two examples that I like to use to illustrate this. So at FCC-hh, we would have 10 billion Higgs bosons, and that would allow us to study extremely rare behavior. For example, in Higgs plus jet production, you can do a very simple MAGRaph sort of calculation, and you can see that you can produce Higgs bosons with PTs as large as 7 TeV. So in other words, these are highly, highly relativistic Higgses at FCC-hh. In terms of the speed of light, you see that this is below per mil closeness to the speed of light, proximity to the speed of light. Furthermore, there's so many Higgses that you can even pay the price of very small Yukawa couplings. And for example, for Higgs decays couplings to muons, that coupling would be measured to the sub% level, which is really extraordinary. The Higgs Yukawa coupling to the muons is very, very small number. Measuring that at the quantum level, essentially the sub% level, would really be a remarkable feat, and would tell us an enormous amount about nature and what's going on in the muon sector. And let's not forget the muon sector is increasingly interesting these days as we think about G-2 or some of the lepton flavor universality anomalies in B physics. Okay, going beyond these sorts of broad brush considerations, if we believe, for instance, that there is new physics in nature above the electroweak scale, but not too far above the electroweak scale, then at low energies we can capture the imprint, the fingerprints of that new physics, and using higher dimension operators. And the most important ones for taking us beyond the standard model are the dimension 6 ones. There are two, so there's many, of course, there's thousands, right? And I just want to talk briefly about two that I think are particularly interesting. The first is this operator here. It modifies the Higgs self-coupling, so that we will discuss that. But also it's very special in its own right. It has such high coupling dimension. Any UV completion will have 4 coupling factors in this Wilson coefficient here. And what that means is that it can be inserted into any one loop diagram essentially for any process that's of interest. And even though it's a higher dimension operator, the result will be finite and calculable, meaning that the effects of new physics can be calculable within the IR theory, even at one loop, which is very remarkable. And this one here, which is of more recent interest to me, in some basis, you can change the coefficients of these operators or even remove them by doing field redefinitions. But in some basis where this is non-zero, it's essentially capturing modifications of the Higgs propagator. They're also very special because they're essentially unexplored, and at the LHC, we will not have any sort of a comprehensive picture about them, so we need to go to future colliders. The sixth operator modifies the Higgs self-coupling, essentially because it's modifying the cubic term in the scalar potential. The mass is the quadratic term. The cubic term is parameterizes the sort of local curvature essentially of the scalar potential, and it captures the Higgs self-interaction. And at future colliders, future circular colliders, we can use this, we can hope to probe this deviation by doing Higgs pair production at a proton-proton collider, or if you could, this is really for linear colliders, linear lepton colliders go to very high energies and pair produce Higgs bosons. At hadron colliders, the most promising final state is BB bar gamma gamma. And looking to the future, this could lead to extraordinarily high precision measurements. So at FCC-hh, you get down to like the 5% level, which is really starting to probe the quantum structure of the Higgs potential, which is, in my mind, just astonishing. And even before that, at circular colliders, at, for instance, FCC-ee, you can use this fact that I mentioned, that you can put this operator into one loop diagrams and look for precision effects coming from radiative corrections, and using those, which are slightly more model dependent, you can probe the Higgs self-coupling at around this sort of 20 or 30% level. So starting to get towards that sort of baseline of being able to say that we've really sort of measured it and we know it exists. Okay, quickly going on to another aspect, which is very, very reminiscent of the LEP era. At the LEP era, we were very interested in these precision electroweak parameters, which were essentially encoding deviations in purely the electroweak sector by looking for deviations in essentially the gauge boson propagators. You can do a similar thing with the Higgs. This is something I studied recently with collaborators in this paper. And the entire program essentially carries through in terms of the theoretical structure. If there's new physics that's just in the Higgs and electroweak sector, it will generically tend to give you deviations in the Higgs 2-point function, which is essentially capturing how the Higgs propagates in that basis. However, unlike at LEP, what we have to do at the LHC is, or at hadron colliders, is much more difficult. You have to take the Higgs boson off shell, and that's hard because it's much harder to produce a Higgs boson. So the most promising final state we covered was the 4-top final state. And we can measure this H parameter, which is like an analogous parameters of the W and Y parameters of the LEP program in terms of the Wilson coefficient in this way and the effective theory cutoff. And you can see that at this is the H parameter on the left-hand scale, but more importantly are these contours of constant C box. And you can see that with high luminosity LHC, you can really not yet meaningfully start to probe interesting theories. These theories are very non-perturbative for any value of the cutoff. However, if you go to 100 TeV collider, you can do much better, and you can really start to probe perturbative physics, perturbative new physics, which is in the Higgs 2-point function. And I think this is an important lesson. In my mind, I think too many people in our community are too quick to say that the Higgs is standard model. Like, there are corners of Higgs physics that we just cannot touch without a future circular collider, and it's not a fair representation in my mind to say that the Higgs is standard model-like because we've measured that the Higgs gamma-gamma coupling and the Higgs ZZ coupling is to within 10 or 20% of the standard model. That's one coupling, that's one corner of Higgs physics. There's a vast, Higgs physics is a vast landscape, and the only way we can ever know if it's standard model-like or not is to probe that entire landscape and really explore it thoroughly. And it's clear that to do that requires future circular colliders. Okay, I should wrap up very soon. One last big picture question I think is important to ask is the Higgs fundamental? Essentially, what's the Compton wavelength of the Higgs? And precision measurements are ways of sort of probing this compositeness, just like when you measure dipoles of atoms and things like this, you're getting a probe of what the substructure of the atoms is. And similarly, by constraining higher dimension operators that involve Higgs physics, we're probing various different angles on how composite the Higgs is, whether or not it has substructure. There's more to that, though. There's more to life than that, though, because not only do we need to measure Higgs properties precisely to see if it's composite, but if it is composite, then we expect to see other resonances showing up. After all, the pions are composite, and soon enough, the rho mesons, for instance, show up. They come along for the ride. It's not really possible to have a composite Higgs without some other resonances showing up. And so searching for heavy resonances also probes this question. And you can see on this plot, in a plot of two parameters that sort of capture the compositeness, the scale of compositeness and the UV coupling in whatever some theory would be, some UV theory would be. You can see that FCC-ee plus hh can really probe a lot of parameter space, both in direct searches for these heavy resonances and using precision probes. And you carve out this parameter space here. So these are the direct searches here. So as the mass scale goes, sorry, my kids are in the background. As the mass scale goes up, more parameter space opens up, of course, because it's harder to probe. But then the motivation for the Higgs being composite becomes weaker and weaker because you have to fine-tune these theories more and more. One last possibility is that the Higgs could be fundamental down to small scales, and if so, then supersymmetry is one of the best candidate theories for stabilizing the Higgs so that it can remain fundamental down to very small scales. And we can see here that FCC-hh can probe the existence of supersymmetric particles up to very high mass scales indeed, and so that's an extra piece of information we would have, discovery potential, or also telling us a lot about the UV structure of the Higgs sector. Okay, so I will wrap up there, and hopefully I've convinced you not so much that I know all of the facets of the Higgs program at Future Circular Colliders, but that it is extraordinarily broad and interesting and gets at the heart of some of the biggest questions we are interested in. Thanks.